Watch these droplets. They pull right out of the air. No fans, no condensers, and no connection to the power grid. People try capturing atmospheric moisture using black shade cloth or open fog nets, but they fail. Ambient warm air flows right through the open mesh, and the Earth radiates thermal energy directly into the underside, erasing the localized chill you need to trigger dew. This illustrates the mechanics of passive radiative cooling. Tuned materials reflect solar heat and continuously radiate thermal energy straight up into the atmosphere. This allows the collector surface to drop up to 8 degrees Celsius below ambient air temperature. Drop below the dew point, and vapor becomes liquid. By harnessing that physical reaction, you can harvest up to 5 liters of pure water every single night, entirely off the grid. To maintain that thermal depression, we need a rigid frame. Step 1 is assembling a skeleton using 2020 aluminum extrusions and heavy-duty 3D printed joints. For low structural brackets, you must use ASA or carbon fiber-filled PETG filament. Standard PLA will warp under the intense summer heat, but ASA prints hold their shape against thermal cycling and severe UV exposure. Next, we have to mitigate galvanic corrosion. If you drive bare steel bolts directly into the raw aluminum extrusions, the ambient humidity causes the metals to react, and the joints will rapidly rust out. The fix takes 2 seconds. Slide a nylon isolation washer onto every stainless steel bolt before you thread it into the frame, entirely separating the two metals. We build this skeleton as an inverted V, tilting the collector wings inward at exactly 30 degrees. This specific angle prevents microdroplets from pinning to the surface. Gravity pulls them down instantly, clearing the area so new droplets can form. This exploded diagram breaks down the 4-layer composite panel that actually catches the water. We have an optical radiative film, a conductive aluminum heat spreader, an XPS foam insulation core, and an aluminized mylar radiant barrier. Starting at the bottom, the diagram shows the mylar and the R5 XPS foam blocking the upward movement of ground heat. Soil holds a massive amount of thermal energy overnight, and these 2 layers stop it from reaching our collector. Moving to the top layer, we apply a barium sulfate-infused film. This acts as an aggressive mirror for the sun during the day, while at night it continuously emits its heat straight out into deep space through the 8 to 13 micrometer atmospheric transmission window. By cutting off the thermal path from the warm Earth below and pointing an infrared emitter at the sky above, the surface temperature plummets. The surrounding air hits that cold boundary plane and deposits its water vapor. To catch that runoff, we slide a single, custom-folded sheet of 99.9% pure C11000 copper down the center spine, set on a gentle 2-degree downward slope. You'll see older designs use open PVC pipe for this step. That creates an exposed, stagnant trough where algae blooms take root and mosquitoes lay eggs. Solid copper solves that biologically. The surface continuously releases trace copper ions into the runoff. That specific ionic contact breaks down bacterial cell walls, maintaining a sterile water path without requiring bleach or chemical tablets. Now, drop the completed thermal panels into the aluminum tracks. Take a tube of neutral cure food-grade silicone and run a thick bead along the entire perimeter. Those seams must be 100% airtight. Even a millimeter gap allows ambient warm air to draft up underneath the panel, ruining the severe temperature drop we built the composite layers to achieve. This cross-section shows the final aerodynamic addition, 50mm clear polycarbonate strips bolted to the upper outside edges of the frame. The lips deflect fast crosswinds up and over the top, trapping a dense layer of localized cold air directly against the condensation film. Without that boundary layer, a light breeze strips the cold away. By physically blocking the wind shear, the microclimate stays completely stable, allowing water to condense continuously until dawn. For the barium sulfate film to reflect sunlight efficiently, the surface must stay entirely free of dust and pollen crusting. This diagram details a completely unpowered rinse cycle driven by a solar thermal wax actuator. Inside the blackened cylinder is a core of temperature-sensitive paraffin wax, mechanically linked to a piston. At dawn, as the ambient morning temperature hits 24 degrees Celsius, the wax melts and expands. That physical expansion pushes the lever, popping open a spring-loaded valve, dropping a uniform sheet of clean water across the array. That rinse water, along with the entire night's dew, flows down the copper gutter and into the primary drain pipe. At the base, the pipe feeds into a PVC first flush diverter. A small vertical chamber traps the dirty morning rinse water and heavy pollen. Once that chamber fills up, an internal float ball seals it off, diverting the pristine condensation horizontally into your main drinking reservoir. Utilizing the physical expansion of wax and the simple weight of water guarantees a daily clean and store cycle. No delicate digital moisture sensors, no electric water pumps, and no batteries to degrade. By sunset, the V-trough is completely passive. The surface chills, the boundary layer settles in the crosswinds, and the droplets run into the copper chute. Hitting that 5-liter yield heavily depends on the season. During a peak summer in Southeast Texas, the high absolute humidity means a single cubic meter of air holds about 25 grams of harvestable water. This chart compares total available water between seasons. When a winter cold front drops ambient temperature to 7 degrees Celsius, the air shrinks its carrying capacity to just 7 grams of water. No matter how efficient the collector, the atmospheric supply temporarily dries up. By combining precise aerospace thermal materials with entirely mechanical maintenance systems, you eliminate the rot, rust, and daily labor of standard setups. You get a static frame that operates as a reliable atmospheric well for the next 20 years.